today he will talk. He is an ICAM postdoctoral fellow, and today he will talk about shape control of colloidal interactions in nematic liquid crystal. Let us welcome our speaker.
Thanks for having me, guys. So I'm going to talk about a project that started last winter in Ivan Smolev's lab at Boulder, and we were collaborating with Tom Mason at UCLA. I don't have a pointer, so we were working in collaboration with Tom Mason at UCLA. I'm now there in the second year of my postdoc. And so I'm going to tell you about colloidal interactions in nematic liquid crystals and how you can control them with the particle shape. And so this is just a not-so-brief outline of my talk. I'm going to give some background and motivation into colloidal interactions, how you generate anisotropic colloidal interactions. I'll have to tell you a little bit about nematic liquid crystals, okay, which are examples of an anisotropic fluid. And I'll tell you what we already know about spherical colloids and nematics, okay? And this will lead into our work, which involves polygonal platelets and NLCs and how you can control their interactions by controlling their shape. And along the way, I'll introduce you to two experimental techniques, one in which you can image the orientational order of a liquid crystal with a confocal microscope, and another technique that combines optical tweezing with holography to manipulate complex shaped colloids and complex fluids. Okay? And then I'll conclude. So your typical colloidal interactions in common liquids like water, for example, can stem from a number of sources, but typically they're isotropic, at least for spherical particles. Okay, and this sort of limits, right, the sort of structures you can have, the kind of colloidal architectures you can build. And so there's a lot of work done on generating anisotropy in interactions. There's many different ways you can do this. Some classical examples are by applying electric and magnetic fields. These are called electrorheological and magnetorheological fluids. You can imagine taking a spherical particle and chemically patterning its surface. These are called Janus particles, Janus colloids. And there are many, many, many other ways of doing this. Now, another thing you can do is just take your spherical colloid and throw it in a solvent that has anisotropy built into it. For example, like a nematic liquid crystal. When you do this, you get new types of interactions that are elastic or due to the elasticity of the fluid, and they're very anisotropic. So I'm assuming most people here don't know what I mean when I say elastic interaction, so I need to tell you a little bit about what a nematic liquid crystal is. Essentially, it's a fluid of rod-shaped molecules. Okay, so for example, 5CB this is a chemical structure. Okay, it's got this rod-like core, which is two phenyl rings rigidly joined and a flexible tail. And so at high temperature, this compound is a fluid, an isotropic fluid. If you cool it below this nematic isotropic transition temperature, there's a first order phase transition into another fluid phase in which all the rods will line up along a common direction. And we denote the direction with a vector we call n, and it has inversion symmetry, so there's either two heads or no heads, as Randy mentioned earlier. And so this phase, okay, it's a fluid with the properties of a uniaxial crystal, so it can flow like a liquid, but it has anisotropy and it's got electric properties and it's magnetic properties. And at optical frequencies, this gives rise to birefringence. And so the classical way of looking at these things is with polarizing microscopy. Okay, this is just a picture of 5CB under cross-polarized. And so there are two more concepts I need to introduce before moving on. One is that the elasticity of nematic liquid crystals. And so we describe, so you can imagine, right, that over here the molecules are pointing this way, and over here they're pointing some other way. And so we have a field of n, okay, it varies spatially. And so you can write down a continuum elastic theory for nematics, and the ground state is one in which n of r is uniform, okay? And deformations away from uniformity cost elastic energy for this expression called the frame free energy. Okay, there are three terms. The First one is display, pure divergence. And so basically, if you display the field lines, it's going to cost you some energy, proportional to K1. There's a twist in which the director field is uniform in the plane and rotates out so, as you go away from that plane. That's called twist, or you can bend the field lines. Okay? And there's 3 elastic constants in general. They're not equal, but they're all the same order, about a piconewton to 10 piconewtons. Okay? And now in an interface, so there's this thing called surface anchor. And an interface between a liquid crystal and some other material is a preferred alignment for the molecules. And so you can imagine having a surface in which the molecules want to point perpendicular to that surface. This is called homeotropic anchoring. Or a surface in which the molecules want to lie flat. So if you use a polymer layer and rub it, the molecules want to lie flat and line up along the rubbing direction. So if you had 2 such plates oriented at 90 degrees, the fluid would just twist. Okay, you have a pure twist distortion in the gap. And so the basic point is that the surface anchoring gives you boundary conditions, okay, for NMR, and the configuration that the nematic adopts, the field, is going to minimize this energy. Okay? And so now imagine you take a small colloid, a micron scale particle, insert it into an aligned nematic. Surface anchoring is going to give rise to long-range deformations of the director. Okay? And so this has been known for a while. And the point is that if you put a colloid, a liquid crystal, for example, this is showing a colloid with homeotropic anchoring, where the molecules are point normal, you induce these deformations. Okay, and so 2 particles, these deformation fields overlap, and there's an effective elastic interaction. And in this case, this is a dipole. This forms a dipole, and so the particles chain up under dipole-dipole interactions. And so the point is that the symmetry of these interactions mimics the symmetry of the NMR deformations around isolated particles. And so you can have dipoles and you can have quadrupoles, or spherical particles. And for spheres, this depends on a number of things. Okay, it depends on particle size, right? The anchoring, the type and strength of anchoring, whether or not you confine the system, and external fields. Okay, so what we're asking is, what we're after is we're about shape. So you take a sphere, you change your shape, what happens? So the way we do this is we fabricate plate-like colloids with lithography, with photolithography. So we spin coat SU8 on a silicon wafer with a release layer underneath. We expose it in an nylon stepper using a mask, and we develop lift the particles up into some fluid. So this is just images of the things you can make. So you can make really complicated things like letters of the alphabet, or more simple shapes like triangles and squares and pentagons. Okay. And so what we're going to concentrate on are polygons, these triangles, these squares, and these pentagons. We're going to throw them in 5 CV and see what happens. So if you put a triangle or a pentagon in, what happens is one side, it's kind of dark, I don't know if you guys can see. So one side lines up with the alignment direction of the liquid crystal. Okay, you see birefringent lobes, bright texture on all the other sides. Okay, so for odd end, you end up with dipoles. Okay, and even end, you see the symmetric 4-lobe arrangement around the outer edges, whereas the diagonal lines up with the far field alignment direction. Okay, this is actually giving you a quadrupole. Okay, and what's interesting about this is dipoles have never been observed with planar anchoring. Okay, and in fact, you get a dipolar NMR without bulk defects, and so that's interesting. And okay, so one question is, why do you get dipoles and why do you get quadrupoles? If n is odd, you get a dipole. If n is even, you get a quadrupole. And why is that? So I just have to back up a little bit and tell you a little bit about elasticity. And there's an analogy between the elasticity of nematics and electrostatics. And so if you approximate all those elastic constants, those 3 elastic constants being equal, the deformations of n will be a Laplace's equation. Okay, so you can make this analogy between electrostatics and elasticity, basically. And if you think of this particle as a source of deformation, far away from the particle, you can expand these deformations in multipoles, just like you can with charges and electrostatic fields. And so you have a monopole term, a dipole term, and a quadrupole term. Okay. Now the symmetry of nematics tells you that this term is 0 with no external torque. And so isolated particles without an external torque acting on them can only have the lowest order of this term, okay, the dipole. And so in the context of spheres, this is just a picture of the quadrupolar case and the dipolar case. And going from here to here, what you've done is broken the plane of mirror symmetry. That's orthogonal to the dipole. Okay. And so if you think about the ways you can orient a triangle with this anchoring condition in a nematic that's uniform, there are only two orientations that give you dipolar NMR. One in which a side is aligned along the far field director, and one in which one side is perpendicular. These both give dipoles, the difference being this dipole is perpendicular to the aligned direction, this dipole is along the aligned direction. All the others, all intermediate orientations, break both planes of mirror symmetry, generating a monopole, giving you a torque, they're unstable, and they're going to go back to one of these two. And if they go back to this one, presumably it's of lower energy. Okay? And this is true for pentagons, and you can make the same argument for squares. It just gives you a quadrupole. And so, one thing I didn't mention, I should have. So in these textures, okay, it's clear that, this is, the anchoring is planar, okay, on these guys. And here, it's not so clear. This texture, you could have homeotropic anchor, you'd see something very similar. And so, to avoid that discrepancy, what we do is we image the director with a laser scanning focal microscope. And essentially what we do is dope the liquid crystal with this anisotropic fluorescent dye molecule called BTEP. Actually has a very long chemical name, that's an acronym. And so these dye molecules line up locally with the liquid crystal molecules. And we take a laser scanning focal microscope, we insert a polarizer here, and so when you scan the sample, right, at a fixed polarization, you see a fluorescence that depends on the angle between this dye molecule, okay, and the polarizer. And so you get nice contrast. It goes like cosine to the 4. And so, for example, this is a cross-section through a cholesteric planar cell with 4 micron pitch. And basically, the molecules are just twisting, okay? And so you see bright and dark bands corresponding to the bright bands corresponding to the polarizations along the line version. Okay. And so this is, it looks so good, but a high-resolution transmission image of one of these squares in 5 CV. And so what we can do is, scan with the confocal microscope for different polarizations. And if you polarize the excitation light this way, right, you see bright lobes on these two sides, right, and these two are dark. And then you flip it 90 degrees, and these dark and these are bright. And so we unambiguously have this kind of deformation field around the squares. Okay, and so what I want to do is, I want to grab these particles and study their interactions. And so I'm going to tell you a little bit about how we do that. And so we use a technique called holographic optical tweezing. And essentially what we're doing is taking a laser beam and imprinting phase profiles, okay, on the wavefront. And we use a diffractive optical element called spatial light modulator. Okay, and so what you can do is take one beam, split it to 2 beams, focus it through an objective, create traps that way. You can even take, independently, you can take these beams and shape their wavefront so that you basically shape the intensity profile of the trap. Okay, so some of the advantages are, there's no moving parts. You can have up to hundreds of optical traps. You can independently control their intensity profiles, and you can move them around in 3D in real time at a rate of about 15 hertz. Okay. And so how do we grab these things? Okay, so to optically tweeze a colloid there's a requirement that's that the index of refraction of the particle has to be higher than the solvent, than the fluid. And it turns out that SU8, photoresist, has an index that's in between the two indices of refraction for 5 CV, which are 1.7 and 1.5. Okay? So what we do is we polarize the laser perpendicular right, to the alignment direction. Okay, so effectively the solvent has a lower refractive index than the particle, and then we shape the intensity profile of the trap so that this thing wants to line plane. And one thing I didn't mention is that if you just hit it with a point trap, it wants to stand up. Okay, so we want to have these things lying down, and so we use these optical vortex ring traps of the right size to grab them in plane. Okay. Are you serious? Oh my God. Okay. So you can do the same thing with triangles. Okay. And so what we do is we trap the particles and release them and track their motion with video microscopy and measure the interactions that way. And so what this slide is showing you is that these are dipoles. Okay. If you have an anti-parallel and their interparticle separation vectors along the alignment direction, they attract. You flip one around, they repel. And the opposite is true for the other rotation. Okay. And we can also do quantitative particle tracking on pairs of squares in the same way. Now, showing that these are quadruples are a little bit harder. And what we had to do was do this kind of blinking optical tweezer thing where, we fix their interparticle separation at different angles relative to the alignment direction, and release them over and over again, bring them back to the same positions, average out, Brownian motion. And these are results of the same pair of particles at different orientations. Their relative displacements, okay, done this way. And what you can see, this is compared to the forces that you'd expect from two quadruples, and it agrees rather well. And this is my last slide, I think. So what about the distance dependence? Now imagine you have two squares and they're interacting with an attractive elastic interaction. This is the angle that is most strongly attractive. Well, for this fixed angle, the force should decay as 1 over r to the 6th. 1 over r to the 6th. And so basically what we do is take these particles at some separation, release them, track them coming together. And over the course of this motion, the equation of motion is the balance of this driving elastic force with a Stokes drag. The system's highly overdamped, the Reynolds number is extremely low, so we can neglect inertia. And you can solve this equation. It's pretty simple. It's a power law force. You get this power law time dependence. And so this is data for three pairs of squares coming together from 3 different initial separations. Okay, and this works very well. So, all right, let me end there. I'm out of time. And so, just in conclusion, okay, so you put polygons in a nematic liquid crystal, you get a dipole, they have an odd number of sides, you get a quadrupole, they have an even number of sides. We have a good understanding of where this comes from, and we develop techniques to manipulate them, measure these interactions. Okay, so what we're exploring now are different anchoring conditions. Okay, so one thing I didn't really get into is that if you have homeotropic anchoring, you can induce defects, and this is something people are very interested in the soft matter community. Can we tune the strength of the dipole moment by using non-equilateral polygons? Can we make submicron dipoles since there's no bulk defects? And can we make 2D quadrupole crystals? Okay. So I should thank some people like Steve Boulder, Raoul, Ting, Wu, Tai Wu, and Kun Zhao, who's still at UCLA, and of course the people who funded this work. So let me stop there and take some questions.
Questions? Well, if not, we are actually a little bit behind the schedule, so let's proceed with the next speaker. Because she's getting ready. Does somebody have a question? Okay, so our next speaker is Oksana Tishkevich, who is exchange overseas, and she's coming from Cambridge University in the United Kingdom, and her exchange visit was to